and YR, I feel like very embarrassed even to talk about my stuff because it's like very simple, I would say. Simply, obviously, that the university are not able to do very complex things. But yeah, let me just go very quickly and I will try to catch up on time. So the idea of my talk is basically it's based on my DML, so Distinguished Microwave Lecture. Talk about radar. It's compressed into a shorter time, so I reduced the time, and I also had some new material which might be of interest to the audience. So it's about system and circuit design considerations for millimeter wave radar transceiver, and it's kind of let's say a generalistic view on like system considerations. Obviously, due to the lack of time, I will not be able to go deeper. It's just, let's say, very on the surface. And then I'll talk very little about package and antenna considerations, technology considerations, and I will give some design examples. So probably this will be a more interesting part, and some system examples. They basically take the chip and do something with that. First of all, about the radar applications, obviously I do not need to introduce because it's the amount of different consumer applications, not only automotive, is steadily increasing and continuously increasing. And we're talking not only about the classical automotive radar applications like what was presented previously, but also any kind of human-machine interface, like controlling any kind of devices by gesture sensing. And so basically this is more or less what I have been working in the recent years on, and obviously space, motion sensing, presence detection, and also recently also biometrics, like any kind of vital signs recognition. So these are quite hot applications nowadays. When we're talking about automotive applications, everybody thinks mainly about the long-range radar, but then obviously around the car, there are a lot of additional applications. For example, like a smart trunk opener, or also, for example, detection of the bicycles passing by, because some people can drive very fast on a bicycle. Also, Nadav mentioned before the child left behind. This is quite, let's say, hot applications nowadays. So let's talk a little bit about the system considerations. Now, the title of this talk is millimeter wave radar. Now, the question is, when I started doing my PhD, I did my PhD in 24 gigahertz, and this product, let's say, that came out of it, it's still selling quite good. Now, the question is, do we need to go to higher frequencies? And well, it depends very much on the application. And I believe, let's say, for automotive, it's I'm not sure whether going to 140 gigahertz will happen so soon. But for let's say consumer applications, it might be the case. So the reason is going to higher frequencies also was shown by Jürgen previously. We reduced the let's say the velocity. We improved the velocity resolution by going to higher f0. Obviously, we can do it by longer measurement time, but obviously then we lose some possibility to detect faster targets. But by going to a higher f0, we get it for free. There is a wider range, potentially wider bandwidth, and we'll talk just about it on the next slide about this potential bandwidth. And obviously, we have a better potential to have a higher change of the angle at the high frequencies, more sensitivity. So basically, our voxel, so basically our pixel in the volume that we can detect, is becoming smaller potentially at higher frequencies. Then for the radar, let's say which kind of frequency bands are of interest. In the D-band frequency range, there is potential frequency bands which are of interest, which when can be combined, we can obtain a bandwidth of above 10 gigahertz. So let's say the FCC bid is still ongoing, and not only FCC, also in Europe, in ETSI, there are discussions about licensing this frequency band for consumer applications, for indoor applications, and this is why this is potential, let's say, frequency band for maybe potential also for in-cabin sensing. So let's say it seems like in cadence sensing going to 140 gigahertz. So I know that speakers before me also, Jürgen has covered the topic of FMCW against PMCW. That's why I have just very one short slides, and then afterwards we have also Vito, hopefully talking about PMCW and digital techniques. So that's why I'll keep it super short. So let's say the classical technique obviously is the FMCW, which relaxes the A to D converter requirements. However, it makes it much, let's say, more difficult to build a massive MIMO array, while in PMCW you get a massive MIMO more or less for free, just by the code division, orthogonality of the codes. However, you kind of shift the problem into your A to D converters, which needs to be now more aggressive, in a sense, consume more power. So when we look at the, let's say, at the FMCW, what do we need to perform? We have a slow time, fast time FFT, and angular FFT. So this is now gets more interesting, because to obtain this angular resolution, we need several receivers. So we need to build an array, and the larger the array, and this is exactly also what Ophir was talking about, this angle, what we need to obtain this. This makes it difficult in FMCW. When we are talking about the resolution, we are talking about the range resolution. And if you just make a very basic napkin calculation, you would realize that we have a resolution, let's say, using classical frequency bands of maybe a few centimeters. Unfortunately, this is not enough to detect anything, let's say, any small motions. So this is why, particularly for gesture sensing, we are taking advantage of the microdoppler effect, which basically takes advantage of some additional rotational parts around the object. So for example, we have an object which is moving, then there are some rotational parts. Then you have like kind of smearing of the spectrum. And this is the collaboration which was done with Google back at my days, as was full-time at Infineon, collaborating on the Soli project. So basically, you can see here many people doing the gesture, repeating the gestures, and you can see that different users repeating the same gesture, and then it results in more or less very similar images. So basically, if you take advantage of this technique and then you apply some machine learning, you might gain information about more fine features. We were talking about the let's say system considerations for the FMCW system, and one of the, let's say, I would say heart of the system, or there are several hearts of the system. One of the heart of the system is the analog baseband. So in the analog baseband, you can do a lot of things good, or you can do a lot of things wrong. And the point is, we need in FMCW a zero range bin needs to be removed, which corresponds to distance of zero. So it's dominated by crosstalk, and also, let's say, the high pass filter must be added. So you need to remove that part, and then you need some kind of variable gain amplifier, which needs to compensate for the dynamic range. And the dynamic range can stem from a wide range of radar cross sections, and then also from different distances. So different distances, because you have targets at different distances, you can compensate by the R to the power of 4 behavior, and you can do a 40 dB attenuation. So basically, depending on what you want, you can either favor closer targets, or you can equalize the reflection from all the targets. When we get to the A to D converter, first of all, we need an anti-aliasing filter, so before the A to D converter, and then we need an A to D converter. As I said before, the IF frequency corresponds to the range. So basically, the maximum range corresponds to the maximum IF frequency. So this is where we would like to put our, let's say, cutoff frequency of the filter. However, the sampling rate of the A to D converter needs to be at least twice, or rather even 4 times the maximum IF frequency, which is dictated by the maximum range that we would like to detect. What about the SNR calculation? The SNR calculation, signal to noise, is related to the to several topics. First of all, we integrate from minimum to maximum frequency, the thermal noise. Then we have some added noise by the receiver, and then we have some leakage from TX to RX. Okay, so this is the equation from the min and max frequency, and then we integrate the power over the target, which is related to the radar cross section. And then at the end, what we'd like to have, this is the signal to noise ratio that needs to be above certain value. Now, when we look, and actually for each scenario, we need to calculate it. For the particular scenario that was analyzed in this case, we analyzed and saw that in transmit power, because to be able to improve your SNR, when we're looking at this equation, and we substitute this equation to here, we can improve our SNR by improving the transmit power. However, we can see that improving transmit power at starting from certain value does not bring any benefit. So we can see that here transmit power of minus 10 dBm is fully sufficient. In addition, obviously, we need to consider the FCC requirements, or what ETSI, whatever we would like to sell the product. Are we allowed to transmit so much power as we would like to? One more thing that I would like to mention on the system level, when we're talking about the short range applications, we might profit by phase noise range correlation effect, which is explained here, which is basically depending on where is your IF frequency, and depending on how far, let's say, you are from the target, you might profit by the, let's say, correlation of the send and the received signal. If we are looking into the 350 meters, like Ophir was showing to us, then obviously we are somewhere in that range. And then the offset frequency that we are looking at, somewhere in the range of maybe several megahertz, then we are not profiting by the phase noise range correlation effect anymore. So to finalize the system chapter and move on to the next chapter, I would like to show a comparison of the how to realize MIMO on a very small scale, comparison between FMCW, PMCW, and OFDM. So when we use an FMCW, we would like to switch between different transmitters, and typically we would do it over the time. We can do it obviously the band division, frequency division, then we lose resolution. We can use slope division, which will complicate the PLL, or what we can do is the time division. In PMCW, we can use Hadamard codes, and it's, let's say, much more native to use at the same time the entire band and illuminate entire time. So we illuminate the target, and we can obtain very good, let's say, resolution. In OFDM, we get it for free, but then it gets much more digitally intensive. So at the moment, I'm a little bit afraid to move into OFDM. So at the moment, my research works on this too. All right, I would like to go and speak about antenna considerations. When we realize a millimeter wave transceiver for radar, where would we like to put our antenna? Depending on the frequency, and also depending on your technology. What technology do you have in your hand? So let's say in the 60 gigahertz range, we are likely to realize the antennas in the package because we realize very high quality antennas. Above 100 gigahertz, it depends again very much on your possibility to realize a good efficiency antennas, and depends how much your silicon cost. And also on alternatively, would it be cheaper in terms of the insertion loss to go off the chip into the package and then realize the antenna in the package? So basically here the decision is as a gray zone. Let's say going around 300 gigahertz, I would say stay on chip. So when you're talking about the package antenna, we are likely to realize it in the redistribution layer and use the reflector as a resonator, because we will have, let's say, an air is our dielectric between the radiating element and the reflector, and we will have a very good efficiency. However, if we would like to realize an antenna on chip, what can we do? Obviously, we are limited by the substrate waves. The parasitic waves are starting to propagate starting from certain cut-off frequency. Unfortunately, if we take into consideration the height of the chip, which may be in the range of 200 micrometer back grinded, the cutoff frequency will be somewhere in the range of 100 gigahertz, 110 gigahertz. And if we realize a radar at 140 gigahertz, as I mentioned previously, then we will definitely have our wanted mode that we would like to radiate, and we'll have the unwanted mode propagating in the substrate. What can we do? We can actually use a several slot antennas. I mean, this is just one of the techniques. And then when we have an aggressor somewhere here, let's assume we have a transmit antenna on the chip, and we have a receive antenna on the chip, and then we are able to cancel the wave which is propagating along the substrate, and we can combine by making the spacing of lambda substrate. Please note that the lambda substrate is less than lambda in the air, then lambda substrate half, then they are in antiphase, and then we can collect the signal and try to cancel out the propagation, the unwanted signal. You can see here the concept is working. We achieve in SOI technology relatively very good efficiency without any extensive tricks. So let's move to the technology considerations, and Nadav has shown very, very beautifully the cost for the cost for the CMOS technologies and what can we do. As a matter of fact, when we look at the lithographic feature with 130 nanometer lithographic feature, we can in B11 technology, let's say by CMOS technology, achieve a much better FTF max than of a 22, let's say, or comparable at least to one of 22 nanometer. And cost-wise, let's say this is the mask cost-wise, this is less expensive. However, when we go into high volume, then CMOS becomes less expensive over high volume, and then digital integration, obviously. My personal opinion on this, and I represent really my personal opinion, that is a combination of a great, let's say, HBT transistor with excellent RF performance and extremely powerful small-scale CMOS for the mixed signal and the digital part, this would be the winning combination. So basically, if you have a SiGe technology, a bi-CMOS technology, this is kind of the best. What is the problem, let's say, of going into super advanced CMOS technology and realize millimeter wave circuits? That basically it does not scale. What scales obviously is the capacitor density, the digital part, maybe let's say the mixed signal part would scale, but not the RF part. Simply because the distance is dictated by the isolation between the channels, between the packaging balls, and so on. All right, and okay, this comparison between SiGe and CMOS technology. As I said before, you can realize better VCOs, you can realize better receivers, and so on. Let's go and jump into the design examples, and I'll try to go through it very quickly. We have here a 60 GHz transceiver, which published a couple of years ago at the RFIC in 28 nanometer CMOS. You can see here an LNA because we need an LNA because we have a passive mixers afterwards, and the passive mixer because of the flicker noise, right? We realize a VCO at 15 GHz because of the sweet spot of the CMOS technology where you can realize a VCO. And we'll come to it just a few minutes later. We see the analog baseband, which is designed exactly using the technique which I showed before and the considerations I showed before. So you can see here the comparison of the performance, and you can see in 28 nanometer CMOS, you can realize a sufficiently good output power. Let's say at least for consumer applications, it's sufficiently good. I would like to draw your attention to one aspect of the transceiver, which is the LO generation. So when we generate the local oscillator signal, at which frequency do we want to realize our VCO? So we can realize the VCO, for example, we have a radar operating at 120 or 140 GHz. We can realize the VCO at 120 GHz. Does it make sense? I'm not sure. And so this is the question, what kind of frequency multiplier we would like to place, or do we need a frequency multiplier? And shall we realize the VCO at lower frequency and distribute at the lower frequency? And then where shall we put the multiplier? Directly at the load, let's say at the mixer and power amplifier, or what shall we do with this? One problem is actually when we look in here, we need also to split the signal. Depending on the amount of the receive channels and transmit channels, we have a single source of a low, and it needs to be splitted. So we need an active potentially splitter and a passive splitter. So active splitters, they help to overcome losses, and we do need some buffers anyway. They increase the power consumption, and cascading some of the stages may reduce the overall bandwidth, or you might even run into some problems potentially of stability, or if it's decentered, maybe it would not work at all. The passive splitters are nice, but they introduce insertion loss. So here are a few considerations on the LO generation and the distribution. Obviously, would like to have the minimum power consumption, to not degrade the phase noise and not degrade our bandwidth. And here's just a little bit of investigation of what can we do in terms of bridging the distance. So you can see here, this is our VCO, and this is our multiplier. When we look at the length of the transmission lines from the VCO to the first multiplier, we can build here a plot and say, okay, we have a 1 millimeter, for example, of distance that we would like to bridge, and then our multiplier will be by 9, for example. And if it's by 9, so you take 120 divided by 9, so we will distribute it at a lower frequency. And then you can see that you really, at some point, it makes no difference anymore which multiplication ratio you take, because the losses are sufficiently low. And then here the losses, let's say, are compared to different frequencies. Another thing to consider is how much does it cost you to, in terms of the power, to buffer the signal. If your operating frequency is 24 gigahertz and you distribute at 24 gigahertz, and then you put the multiplier, okay, then how much can you win in terms of the power? So your buffer will be only 6 milliwatt. If your buffers are at 60 gigahertz and you distribute at 60 gigahertz, you can see you can realize more or less the same, which is pretty nice. If you go to 120 gigahertz, let's say in this particular technology which we use, then the power is almost doubled. What about the multiplication factor? If we use a multiplication factor by 2, you can see 60 by 2, then our PDC will be 5.4. If we would like to have a 24 gigahertz and times 5, you can see the 57 milliwatt. So we try in a very systematic way to understand what is the best. So to do an all passive distribution, all active, or any kind of combination. Okay. So what you can see here is a very systematic way in which we tried using a figure of merit to try to estimate what is the best. And the winner is, as a matter of fact, to generate a signal at a lower VCO frequency and have a high multiplier factor. And then basically you distribute at 24 gigahertz, and then you can play with the length of where you place your multiplier, okay? And so we obtained here the best figure of merit, which is basically your P out times bandwidth and the least power consumption that we consume in total. If we are targeting the power consumption, only the power consumption, then this is the champion, is to generate at 60 gigahertz and have only a single multiplier times 2. Okay, so to summarize, if we are looking for the lower phase noise, we need to generate at the lower frequency and have a high multiplier factor. If we are looking for a high bandwidth, then direct generation of the VCO at a high frequency. To sum up, we designed using these considerations a transceiver, a receiver with the LO distribution. So we use times 5, and then what we use a multiplier times 5, using an let's say aggressive driving of the amplifier, and using a very let's say a high order filter. And this is the result of this receiver. It was published recently, the solid state letter, and 120 gigahertz radar receiver with using a 5x5 multiplier, and then we achieve a very low, let's say, PDC per RX channel, which is, let's say, very, very good. Then we realize a transceiver at 122 gigahertz. I will not go into details of the circuits because of the time, but I will, let's say, the slides will be uploaded. And we built a demonstrator with this, and a functional demonstrator, and it uses exactly the same technique on the analog baseband as I showed before. And you can see here the antenna performance. It's a functional demonstrator. And the last example I would like to show today is the 140 gigahertz transceiver in 45 SOI technology, which uses the slot antennas both for transmit and the receive. On the transmit side, we use the slot antennas to combine power without using the power combiners. So basically, you drive the two power amplifiers into the slot antenna. And on the receive side, we use the technique which I showed before, where you can cancel the aggressor signal, which is propagating over the substrate, and therefore you can do some cancellation. So the concept of the on-antenna power combining is shown here. We feed, let's say, the power amplifiers at these points, because at the slot antennas, you need to go underneath the slot, right? And the main problem is this, the sensitivity to what happens on the other, let's say, port, right? And you can see, depending on what happens on the other port, your impedance might change very much, whether here at the port 2 we have an open or short or anything in between, then what you see at P1 is very much different. So my suggestion is co-design, and it's a very, let's say, heavy co-design of your active and passive circuitry, and therefore you can co-optimize. So this is the, let's say, the measurement setup for the transmit and receive. So we are not able to measure real transmit power or the real noise figure. We have an equivalent isotopic radiated power, equivalent isotopic noise figure that we can measure. This is a summary. The work was published in B6 recently and currently under investigation for journal. So to finalize my talk, I will show a few system examples of the chips that I've shown here before, and a system realized with this chip. So this is the first demonstrator with the 60 gigahertz CMOS radar in 28 nanometer. And it is designed using the equations which I have shown before. And then you can see the PhD student, Johannes, actually boxing in front of the radar module. And you can see on the range Doppler map the detection of his different movements, body moving forward and backward, hands forward and backward, and so on. I know it's not comparable with the work shown before by Mobileye and other colleagues. I know it's, yeah, but that's what we can do. Let's say this is the profiles of the range Doppler map, and what we can do is actually take those Doppler maps and train the algorithms to detect different types of movement, and therefore we can detect certain features. Then another student of mine has taken a 60 gigahertz radar module by Infineon, and he said, okay, look, we have a range FFT, we have Doppler FFT, and then we have an angular correlation. Why not replace all of that by the spiking neural networks, okay? And why don't we do a target classification directly on the raw ADC data? I said, okay, try it. And then he tried, and he applied it on FPGA. He applied an spiking neural networks. So this is the 60 gigahertz radar module, and this is a lamp that he would like to control using gestures, okay? So you can see here, and what he does is following. He turns on the lamp. He just trained the algorithm to detect the gesture. He changes the color of the lamp. He changes again the color of the lamp. Using this gesture, he kind of changes the intensity. Okay, let's change it again. And by using this gesture, he just turns off the lamp. Okay, and this is all running on raw ADC data in real time on FPGA. So to sum up my talk, I would like to jump into conclusions. My personal opinion, again, I represent my personal opinion, that merging of the radar with the neuromorphic computing to kick out the, let's say, the FFTs and perform raw ADC data, this might be the way to go. And let's say moving to the high frequencies, I do see it, at least for the consumer applications. For the automotive applications, it might come a bit later as well. But yeah, this is what I see at the moment. And then the hybrid antenna electronics, in my opinion, it's a very cool research field. So thank you very much. And we are a little bit over the time. So if there is one question, so let's discuss. I saw there was a question. Consumption is a significant part. Yeah, the power amplifiers, they still remain, let's say, quite a